All right, cool. So yeah, as Mo mentioned, we'll be talking about defending against adversarial attacks in Go. And there's some follow-up to previous work that I've done at FAR. So last time I gave a talk in this room, I actually talked about dance. So maybe I'll apply that by doing this entire talk in the form of interpretive dance. Probably a lot. This is joint work with some other people, Kellin, Euan, Tony, and Adam. So seems like not the letting this on the screen. Okay, cool. Yes, other people have worked on this, so say hello to them if you ever seen them around. Like, for example, Adam's right there. Right. All right, this is all right. Okay, so the question we're trying to answer with this work, or give some evidence about this work, is how hard is it to achieve robustness in superhuman systems? So a lot of people have studied robustness, but not many have focused their study on whether we think systems will be robust or not when they're at a superhuman level. So you might hypothesize that that systems will become robust for free as they get more capable. So maybe adversarial examples that break these systems and show that they're not robust, they could be a result of insufficient capabilities. This is a reasonable hypothesis that some people have. So previous non-dance related work showed that this is not true, at least in the domain of Go. So previously, we trained this cyclic adversary that beat these Go AIs, and Go AIs are a lot stronger than humans at Go. I'll explain Go, like the rules of Go, like a tiny bit. So it's a two-player like board game. You take turns putting down stones, and you try to claim territory with your stones. If you surround some territory with the stones, you get points. But also, if your stones get totally surrounded by your opponents, your stones die and disappear. So it's a game with simple rules, but pretty complex gameplay. And so we found this adversary that, like, here the adversary is the white stones, and it tricks the victim into setting up this circular group of stones. And for some reason, Go bots just misevaluate these large circular group of stones, and they just blunder it, and they get surrounded and completely die. And then now the adversary just controls this entire swath of the board. And okay, so
hey, so that example,
that meeting is being recorded.
It's being recorded. In that example, you have a co in the top right corner. Is that like did that cyclic adversary always require having a co there, or is that just a random feature of this one?
Are you talking about? Let's see. Hold on. Which are you talking about here, or like here or something, or
no? The top right corner, the 1-2 point, right?
Oh.
Black could capture there, and then like white makes sleeper, and then white captures again. And
let me think. I actually don't remember for this original version of the cyclic adversary. In other versions that we trained, there often are like co-fights going on somewhere, or like some Seki situations or something.
Sure.
But I don't remember whether this is, I think this is like not crucial for this original cyclic adversary. But I had to double check the games actually, because yeah, I don't clearly remember.
Gotcha.
Okay, cool. So previous work showed that these highly capable systems are not robust for free, and here's a counterexample. But okay, like, so in this work, we will like try to answer like, are these highly capable systems at least like easily made robust? And we'll still focus on the domain of Go for some reasons I'll explain on the next slide. Okay, but this is the motivation for the work, trying to understand like the difficulty of robustness in very strong systems. Okay, so why look at Go? We look at Go because we think the robustness should be easy in the domain of Go. Okay, I'm also not gonna like super explain what robust means here, but roughly I mean something like a GoBot is robust if it can't be beaten by another GoBot that's been trained for a lot less time. This is sort of hand wavy, but it'll do for now. Okay, so why should robustness be easy in Go? So one thing is it's a very narrow domain. Like you're playing this board game and there's not that many moves you can do. You're just playing moves on a board. So it seems like there shouldn't be like that much attack surface in some sense. A second reason is kind of technical, but it's that zero-sum games like this board game are naturally adversarial. You sort of expect worst case to be the triple case. What I mean by this is like if you're playing a board game against me where your win is my loss, then you're sort of incentivized already to try to exploit me, and I'm incentivized to defend against you trying to exploit me. So the normal state of things is already this sort of adversarial setting. So in some sense, like trying to play a game like Go well should already be trying to defend against exploitation. Last point here is that GoBots are a lot stronger than humans. So even like 8 years ago, superhuman or GoBots were able to beat top Go players, and they're even stronger now. So maybe if you have pretty good capabilities, you have like good representations for learning to defend against various attacks or something. So in some sense, we're like trying to stack the cards in our favor. Like if there's any domain right now that we should be able to achieve robustness, it should be Go. Okay, so what did we actually do in this work? Well, we sort of find that building robust Go systems is not easy. I actually meant for this plot to show up later, but whatever. So what we did is we examined 3 different strategies for trying to get more robust GoBots, and none of them really worked. Like all the bots we produced were still vulnerable to attack. There was some partial success that these bots, they play by doing some internal search, and they do become harder to attack when they do a large amount of search. And so that's what this plot is showing. Like before we put defenses on the GoBots, you can exploit them up to like really high amounts of search, and then after it becomes a lot harder, but you still get like non-zero amounts of win at like a non-trivial amount of search. Yeah. Question from Daniel?
Yeah, so in that plot, it's not search. Are you varying the amount of search of the victim, but holding adversary search fixed? Or are you scaling quite simultaneously?
The former. So adversary search is fixed and victim is scaling up.
Okay. How much search does the adversary get?
It gets 600 nodes of search, which is like some, I guess, here or something.
So it's roughly where the orange flags, let's say, 50%.
I get it's a little after.
Sorry, 600.
Yeah.
Oh, okay. Right. Never mind.
Yeah. Okay, cool. So those are our findings, and the rest of the talk will be giving some detail about this. So we tried 3 different strategies, and I'll discuss them in detail later in the talk. But first, some background information. So very quick, all our experiments are based on Cadigo, which is this open source Go system that's the strongest one out there. That's open source. So I'm going to mention Cadigo a bunch of times, and this is just referring to the system we're attacking. I also need to describe a little bit what the structure of these GoBots are. So they all use this AlphaZero style training and architecture. So the architecture is, okay, you have some neural net, and it's always like a convolutional neural net. Now, what do you do with this to train it? Well, you can like make your neural net stronger by doing some search on top of it. So you search down the possible moves on the board, and you apply your neural net to each of these different possible moves. And this is a way to bootstrap yourself to be a bit stronger. So you play a bunch of games against yourself with the stronger version of yourself, and then you train yourself to imitate the stronger version of yourself. And so now you get this version of yourself that's stronger, smarter, funnier. It's the neural net your partner tells you not to worry about. And then you can like repeat this ad infinitum. So you start with a version of yourself, you get a version of yourself with like one muscly arm, you put the muscly arm version of yourself to the left, and you do this again, you get two muscly arms, and you repeat this like a gajillion times until you're just a mass of arms, I guess. Okay, so this is the structure of all these GoBots. And then the way we train the adversary bot is actually pretty similar with some modifications, but I won't go into that in great detail because it's not actually important for the content of this talk. Also, this search over here, it's quantified by visits, which is just the number of nodes you search down in the search tree. So if I say visits, I'm just saying something about how much search. Okay, so that was the background. And now I'm going to discuss the first of the strategies for robustness that was attempted and did not work. Okay, so adversarial training, classic defense technique against adversarial examples, also state-of-the-art. And it's a very simple idea, actually. You take some adversarial examples that you do poorly against, and you add them into the training data, so you train against them. Okay, so this is not our work, but Cadigo has been doing some adversarial training for the past year and a half. So since the end of 2022, we disclosed this cyclic exploit to the developers of Cadigo. And then since then, Cadigo has been initializing every like 1 in 1,000 games of self-play from adversarial positions that were based on the cyclic exploit and then modified with some hand modifications to give a few variations on it. And then since then, also new positions have been added periodically whenever users of Cadigo report that they were able to beat bots with some new cyclic attack. Okay, so this should like train you against a bunch of different variants of cyclic attacks. So we want to see whether after so much adversarial training against a variety of cyclic positions that this Cadigo generates a bot that is resistant against at least cyclic attacks. So we took the strongest model at the end of last year, and we found that it's still vulnerable to attack. So we took our original cyclic adversary, we fine-tuned it, and it's harder to attack, but you still get win rate up to like a pretty large amount of search. So at 8,000 visits of search for the victim, the adversary gets like 60% win rate. At like 60,000 visits of search, you get like 30% win rate. So it's definitely getting harder to attack, but it's still vulnerable, and it's still doing some kind of cyclic shape. Okay, so that's what I want to say about this. Another remark is the cyclic shape made by our adversary is very similar every time, and maybe this is some partial success in terms of like there's perhaps evidence that the amount of attack surface on these models is at least becoming reduced because there's not much variation showing up here. Okay, but actually another thing I wanted to mention is we actually found an attack against the same model that's actually non-cyclic. So this is interesting just in terms of it's showing that maybe if you defend against cyclic attacks, you're still not done. There's a variety of attacks out there. So I'm going to explain this kind of briefly. It's not going to make that much sense if you don't already know the rules of Go. But so yeah, you're welcome to tune out for the next 2 minutes if you just don't really care. But yeah, so here's an example of this non-cyclic attack. So here the adversary is black, and the victim, that's a very strong Go bot, is playing white. And so white plays next in this. Okay, so you want to be paying attention to this group of stones up in the top here, the top middle. So white's gonna play in that position marked with a triangle. And this is a sort of strange move because black can capture back by playing to the left of that and capturing those two white stones. And now, okay, the adversary has captured 2 white stones. The thing that white sort of naturally, like, quote unquote, wants to do is you play in the square marked with an X. You actually can't do that because that repeats a board state. That gets you back to this board state over here. And there's a rule in Go, Co and Super Co, that in order to prevent infinite length games, you can't repeat a board state. So this is actually, the square marked with an X is actually illegal. So white plays to somewhere else. And now black plays in that marked square. And so black, the adversary now, actually because of these 2 points marked with blue, this group of black stones is actually impossible to surround. It has 2 eyes. And so actually black just gets all the points up here marked in blue. So it just gets 15 points right here. And actually, this is not the first time black did this in this game. It actually did this over on the left earlier in the game too. So by doing the strategy of getting the victim to gift it 2 stones and then letting it save a group of stones, like black was able to like net like 30 squares of territory. So this is this new non-cyclic attack. Okay, and this attack actually does not work at high visits. But at 500 visits of search, it gets like 80% win rate. Yeah, I would not say this is like a brutal vulnerability just in terms of like it's defeated by law of search, but it's giving some sort of signal that you might not be done when you think you are. Like it's not just defending against cyclic attacks. Okay, Daniel.
What rule set was the victim policy trained on?
So the victim is trained with a variety of different movesets. This particular game is played with Trump-Taylor rules, so it's, but in general, the victim is trained with like, it varies like different combinations of scoring rule, co-rule, whether capturing your own stones is allowed.
But rule set like obviously.
Yeah, I think, yeah, so like, yeah, so it's doing area scorings list, like,
it's secret.
Yes, that's right. Okay, cool. That's what I'm gonna say on that. So, okay, Categgo did this adversarial training. We wanted to see whether we can do our own adversarial training to do something better. So, okay, I guess what you can say about adversarial training is that at least it defends very well against the original cyclic adversary, but we were able to like fine-tune the cyclic adversary and re-attack the trained bot. So a natural idea to try is, what if we iterate defending and attacking? What I mean is you have some example and you train against it, and then you train to re-attack your defended net, and you repeat this a bunch of times. And the hope is, like, if you iterate defending against attack and then re-attacking and then defend against that again repeatedly, maybe you can defend against the whole attack surface area and cover enough ground that you're just not vulnerable, or that the defended model starts generalizing enough to recognize these strange attacks. So that's one difference between what we're trying here and what Categgo tried. And then the second thing we try is that, well, they only did adversarial, or they only initialized 1 every 1,000 games from adversarial positions. What if we're just way more aggressive and like do 20% games? So we're repeating this adversarial training process a bunch of times, and we're also really aggressively upping the percentage of games that are adversarial. Maybe this like gets you better defense. So we did like 9 iterations of this. And well, okay, what are the results of this training progress? Well, the attack did become more difficult. Like, it took more training progress to find the attack compared to initially. But unfortunately, the defense did not, did not like generalize to defend against cyclic attacks, because we were always able to find a new one. Like, even at the last iteration here, it's still some cyclic looking shape. So that's a little disappointing. And to verify that's still vulnerable, we we attack this defended bot from scratch. So what happens? So if you attack from scratch, the from scratch attack actually still finds some cyclic attack. So that's some additional evidence that this is still vulnerable. Now again, this is actually like you have high win rate and a medium number of visits, but the win rate drops to 0 when you increase the amount of victim search. Yeah, I think you could call this like a partial success. Like it's getting harder to attack when the victim is doing a lot of search. But there's probably still room for attack here. And indeed, like some evidence of there being room for attack. I'll answer questions in like 30 seconds. Is that, well, this blue line is attack from scratch. This orange line is the attack we've trained from like doing these 9 iterations of repeat defensive attack. And this orange line is actually getting like 2% win rate at like 60,000 visits of search. So it's shown that even at high amounts of victim search, the victim is still has some attack adversarial. Okay, I saw 2 hands at least for questions. I'll go with Ben first.
Cool. Yeah, I want to make sure I understand the graph properly. It seems like there's a convergence of the defender winning when they are starting to use the same amount of many more visits, or is there still a ratio where the defender is spending more compute than the attacker, even at the like 10 to the 4th? Sorry, I think what I'm trying to understand is like what's the ratio of compute used for like visits in search? That makes sense.
Between the victim and the adversary. So the adversary is using about hold on, what do I want to say here? Yeah, the adversary is using 600 visits of search. So it would, like on the x-axis, it would be like here if the adversary's number of visits were plotted. And I guess I'm actually not sure whether this is like actually relevant or not. It might just be kind of coincidence that this is where things start trailing off.
So it is still like the defender spending order to more in search.
Yeah, over here, like the victim is spending like 10 times more, and over here it's like spending like 100 times more.
Okay.
And then Ian, did you still have a question?
Yeah, sorry. I feel like I've heard you say this before, but I forget. What is a reasonable amount of search? Like, are these small ones like no one would ever use it like this? And at what point is it overkill versus like what people would usually use? Well,
Sure. Yeah, I actually have an extra slide on this. So, yeah, what's a reasonable amount of search? So we're actually like, maybe in some sense we're not like using that much search. But okay, if you do no search at all, you're still pretty good Go player. And if you start using about 100 moves of search, then with a sufficiently strong neural net, you're probably playing at about the level of the top human. And then if you're like playing a computer Go tournament where you have like 60 seconds per move and you have like a dozen GPUs on hand or something, then you probably go up to like 1 million nodes of search. And if you have like a commercially available GPU like an A6000, you probably can get like 1,000 nodes of search per move in like, oh, I actually don't remember how long I think there's in a minute. So yeah, or no, I think there's actually per second, my bad. So to some extent, like 8,000 visits of search is like not that much. It like takes like 8 seconds, but it could still be like annoying in terms of like, oh, like if you're trying to defend against attacks, you now take this tax of like running your model for like 8 seconds rather than like, I don't know, like a fraction of a second. But yeah, that's the order of magnitude here. Okay, we're turning back up to here. Okay, so those are the 2 adversarial training strategies that we examined. Last thing we tried was switching out the architecture with a vision transformer. So Why would you do this? Like, why would you think this would work? So a lot of attacks we saw previously were these like cyclic attacks. And the natural question is like, where does the cyclic vulnerability really come from? So it's a vulnerability that doesn't just appear in CatGo. We found that appears in Lila and Alp, these other two open source like Go systems as well. And then other users have found that you can attack these two other Go bots called Galaxy and Fine Art. So a natural question is like, well, maybe this vulnerability comes from like something in common between all these different Go bots. And what could that be? We talked about this like AlphaZero style training and architecture before. And at least all the open source models use the same like architecture and training process of self-play. And these closed source two other models that I pointed out before, they probably also do this, although I don't think we have official verification there. So what could the common factor here be? Well, one thing is it could be self-play. The other thing is like maybe it's just like neural net. So all these models use convolutional neural nets. Maybe the issue is like convolutions. And why are these convolutional like architectures suspicious? So yeah, convolutional neural nets, also abbreviated CNNs on the slide sometimes. These convolutional neural nets they're biased towards looking at spatially local data. You'll often like see people say they have an inductive bias towards spatial locality. And by this, I mean like at each layer of the net, each like square in the layer is sort of only looking at nearby squares in the layer before. And so you can only sort of like transfer around local information at each layer of your network, at least until you get like fairly deep with your networks. And so some people who have looked at our previous work, including like the developer of CatGo, they were like, well, maybe like convolutional neural nets, maybe they learned some kind of like local algorithm that works usually pretty well because Go is a pretty local game in many cases, but this local algorithm like misbehaves on these like weird large cycles that our adversaries create. So I think it's reasonable to think that like these convolutional neural nets could be the source of these cyclic vulnerabilities. Okay, so how do you like check whether or not this is true or get some evidence about it at least? Is, well, you like swap out the convolutional neural net architecture with something else. And so we swap out the convolutional neural net with a transformer. So transformer has like less of an inductive bias towards locality than convolutional neural nets do. There's a version of these transformers called vision transformers, which are state-of-the-art in image domains. And if you think about a Go board, it kind of is like a 19 by 19 image. So it's a pretty natural thing to try to apply to a Go board. So okay, like you can kind of just take out this convolutional neural net, you throw in a VIT, a vision transformer, and then you train it, and then see what happens. And then the question is like, is your VIT-based Go bot still vulnerable? So yeah, we did this. We threw in the VIT architecture in there. We trained it from scratch, and you can train it to be superhuman. You can probably do better than this, but we got like be superhuman at like 30,000 visits of search. And then, okay, the question is, can you still attack it with like these weird cycle shapes? In fact, the answer is yes. Like, in fact, without any additional fine-tuning, it's still like sort of vulnerable to the original cyclic adversary. Question from Daniel.
Yeah, so the VIT training route, did you just do that yourself, or like I know Kodiga, like I think it outsources some of its computations of volunteers?
Yeah, we just did this ourselves. It turns out this takes like a few hundred GPU days. So it's not like that bad. It takes like a few hundred GPU days to get up like this level of like being superhuman or being top human at like 30,000 visits. You start getting diminishing returns as you saturate your architecture. Yeah. So like, yeah, like Kaggle and Nansen, they're superhuman at like 100 visits of search. It's like two orders of magnitude less. And yeah, this takes a decent amount of compute. Yeah, but training the BIT, it's actually kind of okay. Okay, so kind of surprising thing is that without any like additional training, like our original cyclic adversary actually like beats our VIT GoBot at low amounts of search. Here's like 500 visits of search for the victim, and we're still achieving like 2% win rate there. And at lower win rates, you can get higher. And then to get some additional like proof that like these VIT GoBots are vulnerable, you can fine-tune the cyclic adversary against the VIT model, the same thing you've been doing for everything else. And like indeed you find like yeah, it's actually that's just very vulnerable. Like at 60,000 visits, you get like an 80% win rate. And the drop-off in this slope here is pretty small. So you can probably attack it for much higher visits, but that's expensive to run evaluations for, so we did not. Yes.
So I wonder if we should have expected this, because like, so if you think about the cyclic attack, it's kind of, whether a group is cyclic or not is a global scale property, right? And the original cyclic attack, like it's very sensitive to this global property. Like and I think appendix K of your original paper, you show that like the bot really cares about whether a cycle is broken or not, right? So given that like it only works for cyclic things, cyclicality is a global property, and to the extent that people might have thought that CNNs were about architecture, it would have been because they only looked at patches at once, at least per layer. Should that have like already caused us to think that like vision transformers would also be vulnerable?
Yeah, I think it is like a little ambiguous, although so I mean to some extent like VITs should be like better at like not learning such local algorithms and tracking long range dependencies better. You might still think that like, well, just like these shapes don't appear that often, so the VIT might just still end up learning something kind of local. So I think these are like some factors that push in like opposite directions. That's not clear where this should fall. Yeah, maybe the answer is like you should do some interpretability on the VIT and see whether it's doing something local or not. So yeah, I think it's a bit ambiguous where you should expect what this result should be. Okay, cool. So the thing we can conclude from this is that there's some evidence that the cyclic vulnerability is not some architecture-specific thing. Okay, so those are the three things we tried, and the conclusion I want to say here is that, okay, we tried like two different kinds of we examined two types of adversarial training, one that was done by Kaggle developers and one we tried more aggressively in-house. And we found that it's definitely harder to attack at high amounts of search, but they still seem to be vulnerable. And then this like VIT thing where you try not using CNNs, I think this basically just doesn't help. The cyclic vulnerability just still shows up. So what do you conclude from this? It's like, well, we said that like Go should be an environment where the cards are stacked in our favor. But even there, you find that straightforward techniques don't give robustness. And so maybe in the real world, robustness will be even harder. Okay, cool. So that's the upshot of this work. Last slide is on some potential follow-up work. So, okay. We tried this like adversarial training strategy for defending against adversarial attacks. Maybe you can do better than this. Like maybe you can do something smarter than just simple adversarial training, or maybe like self-play itself, like I talked about before. Like there's another common factor between all these nets is like about all these GoBots is they all do self-play. So maybe you use something cooler and better than self-play, then like you get better. It's more robust by default, or like it generalizes better against various attacks. And so it responds better to this kind of adversarial training we did. So you can imagine like we tried some straightforward techniques, but maybe you can like try something more complex and do better. So that would be interesting to see if you can like in this environment where the cards are in your favor, like demonstrate a technique that like actually works to get robustness. The second thing is, yeah, maybe you can do some like latent adversarial training. So within our iterated adversarial training, the expensive part was actually generating attacks. That was really expensive. And maybe you can like, if you relax the attack vector, then like you can find attacks more quickly or find more weird looking attacks that your defense is going to be able to like generalize against better when it sees enough examples of it. And the last point of future work is, well, I talked about before that like Go is just like narrow domain and that should make things easier. But maybe that's not true. Maybe narrow domains are like actually worse because like maybe if you're just a more general system, you're more robust by like having seen more things, or maybe you like have gained some situational awareness and you can just like see that you're being attacked or something. So yeah, I think you could reasonably argue that like you shouldn't extrapolate these results too much until we see them also prove out in more general systems. Okay, cool. So again, this is joint work with some other people. And so give credit where credit is due. So Kellin is our resident Go expert who did a lot of the game analysis. Euan helped with a lot of the technical writing, and then Tony and Adam have given important like advisory and research correction. And we posted our paper draft up on Slack in the papers channel, so please give feedback if this is work that interests you. Cool, thank you. All right, we have a question from Aaron in the back.
Okay, both in the paper and in your talk, it's slightly unclear why you decided to replace the CNN with the vision transformer. Okay, I get the reason why, but I'm sort of like, you have three defenses that you try. The first two seem incredibly obvious. And then the third, you're like, we're going to replace a part of our architecture with something else. And I'm like, you could have picked any of the parts of the architecture. You have a little bit of reasons for thinking the CNN might be responsible. I'm curious to like hear about that decision-making process. Was it you like tried a couple different things and this like seemed to make sense after like a little bit of trying? Was it that like the alpha, was it that like this other developer person recommended it? What was the decision making that led to focus a cost? Let's see it.
Right. I would say it's probably more of the latter. Like we did not try a bunch of different stuff. Is more an idea we just had of like, oh, several people respond to our original paper by saying like, oh, maybe there's like some CNN thing. We're like, oh, well, we should like see whether that's true or not. So yeah, there wasn't much search on our end. It was more just responding to people's comments on our previous paper.
And
no one can take this away from me.
So yeah, you mentioned a couple pros to focusing on the Go domain, which really makes sense, especially if it's like by default adversarial situation. And so like therefore there's a like seemingly to me big downside, which is that there's not a ton of other robustness work and adversarial work within Go. I don't actually know if that's true, but like compare this to language models where there are like at least 50 research groups working on jailbreaking of some sort. And so it's just like there's like a lot more ideas being tried, and therefore like it's a lot harder to like BS yourself by mistake because like someone else will figure out what's wrong with your idea if you don't. Whereas in a domain where there's not very many people looking, it's more likely you'll have sort of like results that are wrong for silly reasons, or because you only had so many person hours going towards it. Yeah, what do you think about this? Do you think in retrospect this is like fine, or do you think I guess like do you expect the results to hold up? Like how strong is the evidence?
I expect some version of these, or I guess it depends on what you mean by hold up. Like, I think if you looking at the domain of Go, like, I think the results should hold up in terms of like, oh, like, we found these attacks and they just like work and you can execute them on these GoBots. But yeah, maybe we screwed something up with our defenses, although we saw 2 different adversarial training attempts and they both failed, and one of them was not done by us. But yeah, it would be nice if there were maybe more people working on this so they could like double check our work or something. Although I would say that there's another reason why one of the reasons we did look at this domain is just because not a lot of other people have looked at it and we're in a position where we can, because like the reason why some academic labs don't look at this is just like it takes like hundreds of GPU days, which is trivial for DeepMind, but not trivial for your PhD student or something. So I think it's not a coincidence that we chose this field, that it happened to be one that not many people are at. But at the same time, yeah, I think I agree that it'd be nicer to be building on other people's work or have other people's work built on ours. Yeah, some miscellaneous thoughts. I don't know if that actually answered your question, but yeah. Question from Sid.
This is speculative and might be nonsense, but so there was the Zuckerberg interview on the Dwarkesh podcast recently, and he was saying there are 12 types of ways that people try to do bad things on Facebook. There's hate speech, there's bullying, and we've categorized it at this point. And so our moderators just look for these things. Do you think that there would be any way to just tell the model these are the types of adversarial attacks that you should look out for, and then it would explicitly just look out for them? I know that training is kind of explicitly doing that, but maybe just plopping them into the latent space somehow, or just somehow telling it explicitly these are the things to look out for.
Yeah, this probably requires more development if you want to do this in Go. Maybe there's another, or I mean, goes back to this last point here on maybe more general systems can be made more robust. It's oh, maybe you have something that's just trained on more modalities, or you just have an LLM tacked on somehow. Then oh, then you can tell it things, and then you can follow instructions and stuff. And maybe that's a way you can make things more robust. So I would say that there's not an obvious way you could do this immediately with Go. You either have to do more stuff, or you want to study this more general domain and see what things you can say about it. So yeah, I mean, I guess an interesting question that is in that domain is maybe people have already studied this, but yeah, if you tell LLMs what to look out for, they become robust. I think the answer is actually yes. But how robust they get, who knows? Ooh, 2 questions. I'll go with Scott first.
Okay, so the adversarial training is still self-play, right? It's not actually training to play against the adversary.
Okay, this is actually a detail I skipped over, but okay, so we saw 2 different kinds of self-play. One was the one that Caligo did themselves, and in Caligo's case, this was still self-play. They initialized some self-play games from specific positions. In our case, when we did this iterated version, we actually didn't do the same thing they did. We actually played games against the adversary rather than initializing games and still doing self-play. So in our case, we took every 4 and 5 games are normal self-play games, and every 5th game was a game against the adversary. Yeah. Question from Daniel.
Yeah, so this is a bit of a more broad question. Right at the start, you kind of talked about, you sort of framed this work in the setting of how do we understand robustness as systems get really smart, as they get superhuman, are they still robust? And you're okay, so we're going to do this Go project to figure that out.
Sure.
And I don't know, there are lots of kinds of systems that could be superhuman smart, right? For instance, SAT solvers are superhuman at solving SAT frames. And my understanding is that they are robust to weird SAT instances, right? Now, and in this work, there's adversarial policies that you can train for a fraction of the cost, and you're able to exploit these superhuman policies, which is pretty cool. But I guess what does that tell us about other things? Is there even a natural category of robustness just in general that it makes sense to learn about? Is this telling us about anything other than self-play on deterministic zero-sum 2-player board games? What's the wider?
Yeah, I mean, I think this is a little hard to say, because yeah, I think you don't want to extrapolate too hard from some study in a particular narrow domain. Actually did not know about that SAT result.
This is a result. Just assuming that
Okay.
Does it mean that you can't like write down 3 clauses and then trick this like give your brain stat solver? I don't know. Maybe I'm wrong.
Okay.
I'm not thinking of deep learning stat solvers. To be
Oh,
I'm thinking of,
okay.
Like
It's like
actual
some good old branching cut or something.
real things that real people would
Oh, okay, okay, I
real
see.
stat problems.
I think we're sort of assuming the case where like, oh, that's well, I guess I don't need the slides, but I also don't want to reveal my calendar. Well, maybe let's back the slides anyway.
Great.
Yeah.
Concerning.
Yeah, somehow I have no meetings, I still get no work done. That's the real concern here. Okay, so I think we're kind of looking at like, if you like sort of assume that like superhuman AI systems will be achieved by like neural nets, but just by like scaling them up real hard rather than like through like something more algorithmic like a stat solver, then like in that sense you're sort of I think this has more relevance in terms of like, well, like you're looking at these neural nets and whether they have vulnerability. And okay, like this self-play like in search thing is kind of specific, but like in some sense, I think this like should make it easier for the defense side. Just in terms of like again, like the self-play is this like 2-0 something where it's naturally adversarial. And like the search thing should also like, if you do enough search, you should just be like playing optimally. So that should also be something like in your favor. So to some extent, I want to say it's something like the specifics of this case are like more favorable towards defense. So like, no, you don't want to like generalize too hard from this, but like to the extent like you can conclude like get evidence about from this, you sort of conclude that like even the easier situation, things are hard. I think that's about what I want to say from that. Like, I think the evidence, like, yeah, I think you want to make some kind of like small update in your what you think about the general case. But obviously you don't want to like make super strong conclusions about this. Yeah. All right, another question from Daniel.
Yeah, so to kind of push back against that, I think so. I guess since early on, one reaction to your work has been from the RL or like the zero sum game training community, where they basically said, look, we know that like self play is not actually guaranteed to converge to the right thing, and you've shown that this thing trained by self play is not like you can beat it. And maybe this is just like telling us something we already knew all along, and it's kind of a fact about the self-play algorithm. And it seems to me like if that were true, if these really were driven by self-play, then maybe we shouldn't expect these results to tell us that much about like, whether I can like get GPT-4 to hack into someone's bank account or something.
Okay, sure. Yeah, I think I agree that like only doing self-play is probably like not the move. And like, yeah, I think something I'd be interested in seeing, which I guess is sort of mentioned on the follow-up work slide, is like, yeah, I think if someone were to like, yeah, many people have like posted or I don't know, maybe not said explicitly to me. Maybe they've said things like Adam and Tony, but like I guess I've seen things on Twitter where like, oh, if you try this technique, maybe it'll just work. So I'd be interested in like actually seeing evidence of that. Like I could believe it, but I could also like not believe it. And so yeah, I think if I saw a result where like, oh, you try like my cool multi-agent RL technique and it actually just works to defend against stuff, then like this makes me feel like more hopeful about robustness. And that would be evidence in another direction. So yeah, that's a good point. Question from Sid.
What are the domains where people have made the most adversarially robust ML models?
I think I actually don't know much enough about the literature to say useful things on this.
Yeah, I mean it's a tricky question because some domains are harder. I think computer vision has seen the most work, and people have models that are certified as being adversarially robust, which is less impressive than it sounds. It means if your data point is with an epsilon ball of something you'll see during training data and the label doesn't shift, And of course, you're never going to get adequate coverage in the training data, but that's an area where people have at least, rigorous guarantees of something. And then in terms of domains where I actually think it's harder to exploit, actually language models are like probably one of the ones where it's more challenging. Like, computer vision is just like, you can just break everything with off-the-shelf algorithms. So it's just a question of like, how big that ensemble needs to be. Like, is it something where you can kind of notice adversarial perturbation if you squint hard enough? Whereas with language models, I mean, it's still, everything's exploitable, but sometimes you actually have to work there. All right, cool.
Right. Yeah, thanks again, Tom. Now we know that we can come to you not just for dance advice and music recommendations, but also adversarial robustness and also calendar management, apparently. And so, yeah, once again, thank you, Tom. And you'll be around. You've said you invite criticism and feedback on the Slack channel and Slack. So thank you, Tom.